All right, I think we're ready now. CSTN 283, March 8th. Heat loss, heat gain, design load, equipment sizing. So we spent a long time talking about the thermal envelope last week, and it is one of the primary systems of the building, the inside to outside separation, controlling moisture, all the things that it does. The system that works very, very closely with the thermal envelope and depends a lot on the decisions of the thermal envelope is going to be the heating, the cooling, and the ventilation systems. And so need to spend a significant amount of time in the design and calculations of what and how you're using. So basic purpose of the HVAC system are not just to provide heating and cooling and proper ventilation, but also occupant comfort. And a lot of times, if a heating system and cooling system and ventilation is not designed properly, the errors in design will all manifest in things that cause discomfort to the occupant or doesn't provide good occupant comfort. Maintaining the indoor environmental quality, which includes all of those three, and then filtering out all the toxins. And humidity and moisture is definitely a pollutant, an indoor pollutant that has to be managed through the HVAC and ventilation systems. And then any toxins. We spent in Green Building 1, we talked a lot about different materials and the volatile organic compounds and everything from pesticides to solvents and chemicals. And so that's the other big role of the HVAC system. So one of the things we did mention, and this is what we talked about in systems when we talked about efficient operations of systems and how you can nighttime cooling and flushing of a building, and you can reduce the indoor air temperature of a building and still have occupants be comfortable. Based on the Fanger principle, and he was the father of thermal comfort, and he defined how mammals feel heat, and it's not just the air temperature that makes you feel comfortable or uncomfortable in a house. You have what's called the mean radiant temperature, and that in conjunction with the air temperature is how your body actually reacts to the heat. We talked a little bit about radiant heat. I don't know how much you talked about it with Brad, but basically all of the objects in a room communicate with one another. They can radiate heat back and forth, and that's what helps give you that mean radiant temperature. So if the heating and cooling system does properly control not just the air temperature, but the mean radiant temperature as well as the humidity levels, occupants can feel comfortable at a pretty broad range of temperatures. So the other thing, and we'll talk about this again in cooling in a little bit, is moisture, and it plays a pretty significant role in indoor comfort, and we don't necessarily always think about it, but humidity can make you hot and make you cold, and it's the one thing that if you can control properly, you can really, from a building operation standpoint, you can really supply a broad range of temperatures and still have the occupants feel comfortable. So imagine, in the summertime, if you've got very high humidity, how do you cool off? You sweat. And so you sweat, and that sweat starts to evaporate on your skin, and it pulls the heat out of your skin. If you've got very high humidity, you're not going to get that moisture to evaporate. You're going to feel hotter. Inversely, if you've got a lot of moisture in the winter and you've got that moisture vapor and even fine droplets touching your skin, it's still going to try to evaporate and it's going to pull the heat right out of your body. So controlling the humidity can have a big effect on occupant comfort. Starting with, so we'll go through and we'll get to moisture control in the end, but all of these things that we're talking about are designed to get the proper calculations and the proper load so that we can get the right heating system and cooling system designed so that we can provide proper occupant comfort. So it all starts with calculating heat loss and heat gain. Major factors that affect heat loss are going to be the exposed area of the building envelope. And when you're thinking about doing a calculation for heat loss, especially conductive heat loss, you've really got to be able to understand where the building envelope is and all the areas that are actually exposed to the outside. The other big factor is going to be the thermal resistance and the total R value and performance R value of the wall, and then finally the amount of infiltration or air leakage that we have. Primary areas of heat loss, we're going to see through exposed walls. We talked about conductivity, and we'll talk more about that in just a minute on conductive heat loss. Same thing through the roof and the ceilings, and then also through the basement floors. For what we're going to do in simple heat loss calculations, basement walls, below grade walls can be a little tricky to get completely accurate when it comes to modeling the heat loss, but we're going to keep it pretty simple. Infiltration, so we're also going to get heat loss, as we talked about, anytime we've got a crack or a hole, whether it's mechanically derived or whether it's natural atmospheric pressure, you're always going to have pressure differentiations, and so you're always going to have airflow through those cracks and those holes. And then basic attic knee walls. So the big formula on the top is the first one to really understand in what we'll talk about, and that's the heat loss conductive. So how much heat we lose in an assembly through conductivity, and that's going to be the U value of the total area, which we'll go through that. So the U value times the total area, then the delta T, so what the temperature differentiation is between on one side of the assembly to the other, and then over the course of time. So this just a little bit of a refresher there on what the R value is. We understand that, but let's go back through and start. So the first thing before we get the U value, you've got to calculate the area, and we'll keep it really, really simple. So to start off, we've got a basic wall assembly. It's 8 feet high by 12 feet long, and so we can easily calculate the area of it. The next part in doing any of the conductive calculations is getting the wall R value, and again, for right now, we'll keep this fairly simple. You basically take the R value of all the material in that wall and you add them together. So you've got your siding, insulation, drywall, and then there's actually is a real thin film of air that kind of adheres both to the inside and the outside of the walls, and believe it or not, does actually act as a resistant barrier. It's very minor, but you can see the 0.68 credit for that. So fairly straightforward and pretty simple. In order to get the total R value of the wall, you're just adding, it's the sum of all the materials in there R values. Those R values are pretty easy to get. There's a lot of different manufacturers' information. You can get general tables for basic building materials, but it's not that difficult to get the R value of materials. Next step is, because in our formula, U times A times delta T times time, everything's in the U value. We just need to convert it. So U value is simply 1 over the R value, and we get a U value of 0.074. Make sure so we're going to go back. The next thing that you have to do is get your delta T, and if you're trying to calculate conductive heat loss for a moment in time, you're going to want what the indoor temperature is and what the temperature is outside. When we do this in a heat loss calculation, whether it's a manual J or HVAC calc or Elite or whatever program it is, we have what's called design data, and the design data is climate specific, it's location specific, and it's a given number based on the averages of temperatures for that specific area. This is for ASHRAE standard heating design, inside design temperature. 68 is the norm. It's what we use for the temperature that the system should be designed to maintain. Our design outdoor temperature here in Missoula is 3 degrees Fahrenheit. We'll talk about this a little further. But that's the temperature when doing a manual J calculation that we have to use to figure the conductive heat loss of our buildings. And the way that the design criteria is set and where that number comes from is the 99% value. So 99% of the year, the outdoor temperature is above 3 degrees in our design data. So a little over 361 days a year, the temperature exceeds this value, which is interesting because it's based on the manual J calculation in the code. It's the temperature that we have to use to design our systems. It'll make a little more sense, but I'll tell you right now that in my personal opinion, so you don't have to take it as fact or science, but it's very, very inefficient to be designing a heating system to operate at a temperature that we are above 99% of the time. So we're really designing a heating system that's preparing us for the 4 or 5 worst days of the year. That's just my soapbox. I'll get off of it now and get back to the... and so the same thing for the cooling value, using 1% occurrence. So 1% of the time the temperature is over that temperature. You'll also notice a couple other numbers in there. One is the 97.5% occurrence. It's a similar average, except that it's a little more tolerable. I don't know what the numbers would work out to be there, but that's 2.5% of the time the temperature is below that temperature for a design set. So if you design to the 97.5% occurrence, you may have a system that 12 to 14 days of the year may not be able to effectively and efficiently keep you at 68 degrees. Does that make sense? You guys understand where those numbers come from? Okay. So just a quick example. So we've got the the overall U value, and let's just assume we went ahead and we figured up all of our wall components, and we came up with the U value of 0.1. We're using our design temperature of 3 degrees Fahrenheit outside, 68 degrees Fahrenheit inside, and we're just going to figure a basic building, 20 feet long, 40 feet wide by 8 feet tall, with a flat ceiling and a flat floor. So we have our U value. First thing we've got to do is figure our area. So it's a 20 by 40 building, and this is where the area exposed comes into play. That's the biggest factor in the heat loss. And in this one, we're going to assume that this is a insulated wood floor. It's insulated exactly the same as the walls are, and it's not a slab on grade basement. They're all exposed equally. So if we take the floor area by the flat roof area, those are both 800 square feet exposed, and then we've got two 20-foot walls and two 40-foot walls by 8 feet tall, which is another 960 square feet. So we add those together, and we've got 2560, and that's the total in that. If you can envision a 20 by 40 rectangle building with a flat roof, insulated, just a big box, it's 2,560 square feet that are exposed, that create the thermal envelope that are going to conduct directly into the exterior. We got our assembly U value of 10. Remember, we added up all our R values, and then we took the inverse of that. We just got our square footage exposed, 2560, and then our delta T is 65 degrees Fahrenheit. So we had 68 degrees inside as our design temperature and 3 outside. So we've got a 65 degree delta T, and then we're gonna do this heat loss over 10 hours. So our conductive heat loss, our U, 0.10 times 2560, our square footage, our delta T is 65 over 10 hours, 166,400 BTUs over the 10-hour period. Simplify that down, and our conductive heat loss for our little box is 16,640 BTUs per hour. So if we wanted to put a heater in that, we'd know at least how much our conductive heat loss is at this point. But is conduction the only way we're losing heat through our building? Yeah. Does that all make sense for that one? I see no blank stares. Perfect. The second thing we've got to figure out is our convective heat loss, or our heat loss through air leakage. Again, we're doing our heat loss in BTUs per hour. We've got to figure the volume of our building. Because it's a volume of air, we're not talking about the exposed square footage of the building. We're actually talking about that air change. We still need our temperature, and then we need our air changes per hour. So in an existing building, we could do our blower door test and we could get our air changes per hour. A lot of times when we're doing design, we've got to make assumptions for that. And so we don't always exactly know. We can put a target air change per hour when we're designing for new construction, but we don't necessarily always know what it's going to be. The other thing in there, in that, if you look at this convective heat loss here, the 0.018, the heat capacity of air, and I think you guys covered a little bit of that in the first couple weeks with Brad, but basically the amount of energy it takes to raise a cubic feet of air 1 degree Fahrenheit. One thing we have to calculate for is the heat capacity of air changes with altitude. And for convective heat loss calculations, anything over 3,000 feet is going to be 0.0162. And that's what we'll use here for our little example, because that's the number that we use. It does, again, the less density you get in the air, the less heat capacity that it does have. It actually does change, and if you're trying to do this and be very specific at higher altitudes, 7, 8, 9, 10,000 feet, you're going to have even less of a heat capacity of air. So our same building, 20 by 40 by 8 feet. This time we just need to figure the volume. So 20 by 40 by 8, we come up with 6,400 cubic feet. We're going to make an assumption that our air change per hour is 0.3. And that's just an arbitrary number. That's whether that's a target we put in design or whether we did actually test for it. Our delta T, so again, we're using our same design loads, 3 degrees outdoors, 68 degrees indoors, and then over a 10-hour period. So run the math out, we get 20,218 BTUs over 10 hours. So about just over 2,000 BTUs per hour in convective heat loss. So assuming we've got basically a building that's about an R10, we had, what do we have, 16,000 BTUs through conduction, 0.3 air changes. It's neither incredibly well insulated or incredibly super tight, but we still lost significantly more heat through conduction than convection, and that's almost always the case. There's so much area exposed, and especially new construction now, we're looking at the natural air changes of 0.1, 0.2. Conduction is by far what we're getting most of our heat loss through. So the last thing, does that formula make sense? You guys can figure that one out. The last thing we have to do is get our total, and that's simply just the conductive and the convective added together to get our total BTUs. And this is an important calculation. This is a big deal, especially in the residential and the smaller buildings that we build. And we'll talk a little bit more about sizing, because having an accurate heat loss and understanding what the design loads of the building, how much heating and cooling that building is going to take, is a significant piece of figuring out how you're going to design the thermal envelope and what systems you're going to use to heat and cool, and also where you can and can't make the upgrades. So, for example, in this one, let's say, and I didn't bring my calculator with me, but let's say this is an example of an older house, and you're going to go in and do some energy upgrades. You can easily figure out if you change your air, for example, if you're going to air seal it, you're going to change that from 0.3 to 0.1. 0.062, we're still at the same volume times 0.1, 65. So you're going to take that all the way down to 650 BTUs per hour just through air sealing. Does that all make sense? And it's all really super easy, and you can just easily figure a wall and run a conductive heat load and It's good, because then now it just gets infinitely more complicated, and it's back. If we jump back to that slide where we look at this basic wall and we figured out the R value, it was pretty darn simple, but we're forgetting about a whole bunch of things in the wall, and primarily we're forgetting about framing and all the other parts in the wall. So when we figure it ends up sometimes becoming the hardest part of the heat load calculation, is really getting the assembly U value put together. So that last slide that we just looked at, it was easy to get a clear wall R value. We were just making the assumption that these are the things that we have in the wall. With the cavity framing, there's a significant amount of lumber in the walls. Anywhere from 9 to 27% of the wall is wood. And so we know at that point that we're not going to have the same resistance. So what you have to do, and this is where a lot of the programs really come in and can significantly help out in energy modeling, and because you can get these things replicable in the programs, but you have to break down the whole assembly in different sections. You've got to do, and the way that ResCheck works and the way that most of the code programs work, you break down each window almost into its own section. You break down the framing part of the wall into its own section. You break down the doors. Each one of those pieces is going to have a different U value. And then you've got to figure out, based on your total square footage, what percentage of the assembly is that. So if you think back to that wall example that we had that was just a square wall, and that was 96 square feet, if we've got a big picture window in there, and so that wall was an R13.4, if we've got a big picture window in there, that's 10% of that wall, and that window is going to be a 0.30 U value. We then have to add that percentage to the wall percentage. So we have that wall percentage that was, remember, it was a 0.1 U value, and so that was 90%. So we'd have our first U value, which would be 0.1 times 90%, plus our second U value, if that window is 0.30, times 10%, which is, once we add those together, we're going to get an average U value of the whole assembly. Does that make sense? Because you can't just say, because we have our 26 insulation in the wall and add our drywall and add our siding on the outside, we come up with an R28, so our whole wall's an R28. It's not. We've got framing in it, we've got windows, we've got doors. This is just an example of what they call the framing factor, and depending on what framing you're using, there are some shortcuts and averages. You don't necessarily have to go through and figure every single stud that you have in the wall and measure it up and get the square inches and convert them to square feet. And my chart got a little mixed up, but you can see in the first column you've got your stud spacing, and if you do a stud-only framing factor, and this starts with an R14 clear R, so assuming that there's no other materials in the wall, we're looking at an R14 total R value. On the low end, if you just include the studs, call the stud only, you're still looking at, in 16-inch on center, nearly 10% of the wall is framing. And so it's going to effectively reduce your R value down to 12.7. You can look on down to the far end where you see up to a 25% framing factor. And for a standard wood framing, 2x4, 2x6, 16-inch on center, no advanced framing, the wall is about 25 to 27% wood. And so that has to be accounted for in your heat loss calculation. And you can see you're effectively taking an R14 wall down to an R10 wall with your framing factor. So, questions, comments, thoughts? Let me just quickly pause it right here so I can split the recording. And then you can take about 2 minutes, jump up and down.
Wipe that table off, and I was like, I think that's called.